All right, moving on. So we just finished solving logarithmic equations. Let's solve some exponential equations now. So where's our unknown in these examples? You can see our variable x in example A is up here in the exponent. We got to get it out of the exponent. So to solve this exponential equation, of course, we got to first isolate the exponential term. That's step one. So let's go ahead and do that. Let's go ahead and isolate this term here. So I'm going to go ahead and we'll make that note over here on the side. Isolate the exponential term. So let's go ahead and divide out the 4, right? There's a coefficient of 4 here in front of it. So I'm going to go ahead and divide both sides by 4. And as I do that, I have 7 equal to 5 raised to the 3x power. Now, what I'd like to be able to do is be able to rewrite both sides with the same base, and I can just drop down the exponent and solve for x. But with bases of 5 and 7, I can't get those over the same base. So what we're going to do is introduce logarithms to solve it. So that's going to be our second step. All right, let's introduce logs. Let's take log base 10 on both sides. All right, so as we do that, we can also do the same thing on both sides. All right, we're still equal. So I'm going to go ahead and do that. I'm going to do a common log. I can do any log base. I'm going to do log base 10. I like log base 10 because we want to check it in our calculator. We can check it easily. Remember, it knows common logs and also natural logs. So log base 10 or log base e, for that matter, would be logarithms that would be nice to work with. So we make it easier on us to check in the end. All right, so with that said, we've introduced logarithms. So why do we introduce logs? Now, right, as you look at our problem here, right, we've got log base 10 of 7 equal to log base 10 of 5 minus to the 3x power. We're going to use the power rule now. So we're going to finally bring down x. So remember, this is up here in the exponent. So let's apply the power rule. Now I want you to remember, what does the power rule state? Maybe you've forgotten the power rule. Log base a of m to the p power is equal to p times log base a of m. So this can come down in front now as a coefficient. So as we're looking at our equation, right, we've got log base 10 of 7 equal to 3x times log base 10 of 5. So there's the power rule being applied. Right, so you can see we brought down, right, that power of 3x. And what does that allow us to do? Well, that now allows us to solve a linear equation. So we're just solving for x now. So we're going to get x by itself. So we can divide out on both sides log base 10 of 5 on both sides of the equation. All right, so as we're simplifying down, right, we've got log base 10 of 7 divided by log base 10 of 5 equal to 3x. All right, now what do we do with 3x? Well, we still haven't got x by itself, so I'm going to go ahead and get rid of the 3. So let's go ahead and multiply both sides by 1/3. So as we do that, we get x now. So again, solving for x, you need to get rid of coefficient. Maybe you did it in one step. But yeah, I've got log of 7 divided by 3 times log base 10 of 5 equal to x. Right? And there's our solution, right? We could check it at that point, right? We've got our answer. Now, that's the exact value. Now, if you want an approximation, and sometimes they do want an approximation value, we can pull up our calculator. So remember I mentioned earlier, right, as we're solving for x, we like to use common logs or natural logs in our exponentials because it's easy to check. So pull up your TI. We'll go up here and plug it in together. I'm going to type in our answer. So we had the log of 7. So you can see over in the left-hand side of your calculator, we got the log and natural log keys. So there's a log of 7. So we type that in. And divided by 3 times log of 5. So I'm going to put 3 times log of 5 here in the denominator. I'm going to close that out. All right, and I get 0.403. So maybe it asks us to round to the nearest thousandth. Sometimes it'll ask you for a particular decimal value or a rounded answer. So we have 0.403, right, rounded. So there's the exact, right? Here's the approximation. And sometimes they'll want an approximate answer, a decimal answer. So again, a couple steps in that problem. Of course, we had to isolate the exponential term, and then we had to introduce logarithms. So we took log base 10 of both sides of the equation so we could use the power rule and bring down the x term, right? Once we brought it down, we just divided it out on both sides, which we should just went ahead and divided a 3 and log 5 in one step, right, in that problem. So with that said, there's our answer. There's x. Now let's do the same thing, example B. All right, as we're looking at example B, I want to find x. Well, this is a natural exponential. Of course, you see your natural number e, which is around 2.718, right, rounded. So remember math, we have some special numbers like pi and e. This is our natural number e. With that said, we've used e in a lot of applications. We talked about an exponential growth, right? Looking at it continuously. It's modeled by this natural number of e. With that said, I don't have to get x out of the exponent. So our first step, just like our last example, we need to isolate, right, the exponential term. We need to get it by itself. So let's go ahead and do that. So I'm going to go ahead and divide out the 10 on both sides. Get rid of that coefficient. So as we do that, now our equation reads e to the 6x power equal to 7/10, right? And then let's go ahead and introduce our property. So we know with e and 7/10, we're not going to be able to rewrite with same base, so we're going to introduce logarithms. So this time, instead of taking log base 10 on both sides, I'm going to take log base e, or the natural log of both sides of the equation. Since I'm dealing with my natural number, I'll make it simplify nicely. Now, with that said, that will make it easy also in the end to check it on our calculator, because again, we have that shortcut, right? Natural log key on the calculator. So let's go ahead and do that. So I'm going to take the natural log base e, abbreviated ln, on both sides of this equation. So we have natural log of e to the 6x power equal to log base e, or natural log, right, of 7/10. Now with that said, now we're using the property. We could use the power rule if we wanted. But I know that in a logarithm with the same bases, so I'm going to use a simplifying property. We know that log base a of a to the x power simplifies to x. So let's use that. So log base e of e to 6x power simplifies to 6x. All right. So again, that's my same base rule here. Same basis. So we'll make that note here. Applying that property. Simplify. Now, what kind of equation do we have? Now we got a simple linear equation. So we're solving for x. Our last steps, divide out that 6 on both sides, and we have our answer. So what does x equal? X is equal to natural log of 7/10 divided by 6. And there's our exact. So we want our solution. We've got our answer. Now let's go ahead and give them an approximate answer. So remember, go to your TI. Let's pull it up. So in here I've got natural log of 7/10. Again, using that natural log key, divided by 6. I got negative 0.059. We round to the nearest thousandth again. going to 3 decimals. So there's, again, the exact answer. Right? Of course, here's our approximate. Right? So that's solving exponentials. Isolate the term. Right? Try to get the same base. If you can, it makes it easy. Right? If you can write them both sides the same base, you just drop down the powers. Or you can always introduce a logarithm. So if I'm going to introduce a log, I'm going to do either common log or natural log, and then I can apply my properties, whether it be the power rule or your same base rule. In this example, I use the same base rule to solve it. So I hope that helps you. Another good example there from logs and exponentials. So we'll take a break, and then we'll look at some applications of exponentials again to finish out our review.